Hello, welcome students. So today we will begin with our classes on modern experimental techniques. Okay, different advanced experimental techniques in modern physics. Okay, so briefly we call it as experimental techniques. And in fact, this paper consists of different chapters. So the first unit is about vacuum techniques. Vacuum techniques means different methods by which how vacuum can be created in different chambers or different containers. Okay, in which we do different experiments. Okay, we need a vacuum in different containers, enclosures, where we do various modern advanced experiments. Okay, so this is a basic requisite of any modern advanced experiment, creating vacuum. So in this module, we will be talking about various methods used or various machineries, we call it pumps, used to produce vacuum. And we will also deal with different terminologies, terms which are frequently coined in vacuum technology. We'll get some rough understanding about different details of such terms and some basic equations which is known as pump equations, which are very relevant in vacuum technology. So some minor derivations are included. Okay, and the second module is about thin film techniques. Thin film means film, okay, thin surfaces or foils whose thickness is very, very small, of the order of say 10⁻⁻6 or -8, like that, okay, for angstrom order thickness. Thin films are very important in various technical applications, in technology, in industries. Why? Because they show, they manifest so many peculiar or useful phenomena compared to the thick counterparts. For example, one of the most simplest example is that of oil formation on water surface or liquid surface. So, when it is shined with some white light, you get colors. So, instead of the thin film, if you assume a thick oil film, you can't, you will not get such a type of colors. So, that's one of the most common example of the phenomena shown by thin films compared to thick films. Okay. Similarly, there are many optical phenomena, magnetic phenomena, electronic phenomena, or innumerable number of semiconductor phenomena or electronic phenomena. So the people explore these phenomena out of thin films. So the technique of forming thin film is very important. The measurement is very important. These all will be discussed in thin film techniques. And we have the third chapter on particle acceleration techniques, and then you have some basic understanding of particle acceleration, which will be discussed in detail in this particular point. And fourth chapter is on material analysis techniques, something like a spectroscope. Here we will try to study some methods used to analyze samples, materials. In material analysis, what we do, we try to understand by what material a given sample or specimen is composed of. Okay, we will make use of some form of spectra. That spectra will be analyzed, and we will try to find out the content matter of a given sample. Okay, that is the main theme of this unit. And we have the last chapter or last module. This is about X-ray diffraction techniques. In X-ray diffraction, this again is yet another method of material analysis, in which X-ray, specifically electromagnetic X-ray, electromagnetic is used. That will be released on certain samples, and the sample will produce its own spectrum. We call it X-ray spectrum. That X-ray spectrum can be analyzed. From the analyzed reports, we will get many important information about the sample, its speciality, different other material parameters, draw out of the data. Okay, so these are the 5 different modules contained in this particular paper or in this course. Okay, starting with vacuum techniques, as I told you, which essentially deals with vacuum machines, or we can call vacuum pumps. There are so many varieties of vacuum pumps. Each one works on its own physical principle. Each are of unique methods. Okay, so we have to study them separately, and we have to also study about measuring devices. Once we produce vacuum, we should be able to measure it. Okay, so measurement is another area of vacuum techniques. Okay, measurement itself is a technology. Production is another side of the vacuum technique, and measurement is again another side of the vacuum techniques. And we have components, accessories, which are essential part of any vacuum system. So many accessories. Accessory means any associated components, okay, linking parts, organs, you can say, which are required to assemble the system. They all come under accessories. Okay, understand? We will talk in detail about those accessories whenever we touch upon this particular unit. And here is the thin film techniques. As I told you, thin films are entirely different from the thick counterparts. They give us so many physical phenomena, like physical events, effects, so that can be made using different our modern gadgets, ranging from our simple mobile phone to satellite systems. They make use different applications. Okay? So thickness has a special role in the production of physical phenomena. Okay? Thickness and phenomena are directly linked. As the thickness decreases, they start showing different interesting phenomena. So its thickness measurement is also very important. So if thickness is not known, the study will be incomplete. And the thickness measurement is also a big technology. Understand? Just like what we told about vacuum technology. Vacuum measurement is a technology and vacuum production is another technology. Similarly here, fabrication of thin film is one side of the technology, and measurement of the thickness of such films is another second side of this technology. And you can, once the films are fabricated, its properties has to be studied exhaustively. This is also an important aspect of any thin film technique. Okay, thin technology, you can say. In particle accelerators, already you have in your lower classes, you have come across with different particle accelerators. Here we will make a detailed study about different other accelerating methods, including in the design of various accelerators. Design means how it is made up of. And working principle is very important. Okay. Each device works on its own unique principle. Okay. Different techniques are based on different physical principles. That will be thoroughly dealt with in this chapter, and we will also see some of the typical uses of such accelerators. Understand? And here is the fourth unit. Is about material analysis technique or elemental analysis technique, which is specified here. Okay, because we are analyzing essentially elements, element by element, or you can say atom by atom, atomic level analysis. Okay. Also call it atomic analysis technique for that matter. Here we will study different techniques like PIXI. This is called proton-induced X-ray emission spectroscopy, and the second one is NAA. Okay, it is nothing but neutron activation analysis. Okay, we have a detailed study about it, and thirdly we have Rutherford backscattering spectrometry. This way you have 3 different methods. Each method will be studied in detail. Its instrumentation part, how the apparatus is made up of, the setup is made up of, its working principle, and its modus operandi, means the way of doing things in it. Okay, that will be dealt in detail in this particular module. And the fifth unit is about X-ray diffraction techniques, which some basic ideas you have already got in your school classes. Here again using the Bragg's law. It's a basic principle, the diaphragmometer, and certain other theoretical area like the Carroll equation, phase study, crystalline study, like so on and so forth. Okay, so this is another last module of this particular course. Let us start with the vacuum techniques. That is the first unit, in which we will be doing different terminology, different terms used in vacuum, and different pressure units. There are so many pressure units. Okay, made use in vacuum technology that will be familiarized, and the classification of pressure designs. Okay, there are different designs in vacuum technology. Different application needs different designs. So we will have a look at different pressure designs in vacuum technology, and some applications of vacuum technology we will also discuss. And the core area of this unit is about the study of different types of pumps in working, its design, okay, construction, like that. Okay. So these are the main content of this particular unit. Starting with the vacuum technology. Vacuum as literally means what? Any space devoid of matter. Any particular area, space which contains nothing. Okay, nothing. But that is only a literal definition. But in practically, it is not possible. The perfect vacuum is a very ideal concept, a theoretical concept, and very rarely possible. Hardly possible, you can say. And you can define vacuum technology as a branch of science or engineering which deals with the production, maintenance, and measurement of vacuum. Understand? So it involves production, vacuum production, how it is produced, and the machinery, different pumps, and subsequently you have to maintain that pressure. That's also very important. Okay, once produced, it cannot be maintained if your technology is not good. Your chamber is not properly isolated. Okay, it should be properly leak-proof. So these are all different concerns in maintenance part. Understand? We need such containers. So design of container, its construction, material selection. These are all important. And finally, measurement. Okay, for different experiments, you need different designs of pressure, different ranges of pressure. Every experiment you cannot do in a particular pressure. Okay, so different designs are used for different type of experiments. That has to be explored, okay, researched. So these are all concerns of vacuum technology. Understand? So in a sense, vacuum technology is the production, it is the maintenance, and measurement also, and other associated results, finding out of new materials, new gadgets, new devices. They all come under vacuum technology. And technically, what is vacuum? It has been scientifically defined by American Vacuum Science Society in 1958, one of this conference. And according to that convention, according to that the definition, it is defined like this: a given region of space filled with gas at pressures below the atmospheric, having a density of 2.5 into 10⁻⁻10 molecules per centimeter cube. Okay, so this is the technical definition of vacuum given by American Vacuum Science Society. Okay, so it clearly indicates that vacuum doesn't mean that a space is devoid of matter. Okay, it is not devoid. Okay, it contains some molecules. Still, you can term it as vacuum. Okay. Only thing is that the space should have a density, molecular density, less than 2.5 into 10⁻⁻10. That is also a good enough number, but still you can count in space which contains less than the number can be practically considered as a vacuum. Okay, so that's the first and the foremost concept coming in vacuum technology. Okay, historically, if you see the history of vacuum starts with the invention of Harron's syringe, one type of syringe, by pushing or pulling the shaft inside it, you can pump water out. Or understand? So that is called piston. Okay, by piston, you are well familiar with such cylinders in which a piston can be moved forward or backward, and the appropriate vacuum can be created. Okay. So that's the foremost invention in happened in vacuum. And in 1680, Galileo developed the first suction pump by mechanical pump by using hand manually. We can rotate some lever and we can create vacuum, and the liquid can be sucked up. Okay. And in 1643 AD, Italian scientist Torricelli, evangelist Torricelli, discovered atmospheric pressure, or he measured atmospheric pressure by using mercury pump. The well-known experiments, you are familiar with it, so I don't make an effort to explain it. And in 1650, German engineer Otto Hahn invented the first mechanical air pump. Okay, that one which you all are familiar with, and the modern, most of the modern electric pumps, water pumps, are example for this mechanical air pump. Okay, and in 19th century, so many other discoveries happened, like the discovery of electric motor, electron tubes, electron cathode ray tube, ionization, cryogenic techniques, in which you can produce very low temperature. Okay, once a low temperature is produced, what you can do? You can solidize different gases. Ultimately, in pumping, what you are doing, you are removing, you are expelling, displacing gases. So instead of displacing gases, you can simply cool down and you make it in the form of solids. So that way also you can remove gases from a given container. Okay, that is called cryogenic technique. And in 1904, DEVOID, he used specially activated charcoal, carbon composition. If you cool it down, its capacity to absorb gases becomes very high. Okay, the absorption rate is very high. So that way you can pump out gases. In 1906, Wolfgang Gale built the first rotary pump. Okay, with the first rotary pump, that was a very important landmark in this vacuum technology. Was a German engineer again. He designed another one in 1911 known as molecular pump, in which a certain liquids was used, having high molecule liquid was used. By liquid, he could pump out gases. Okay, we will study in detail about this kind of pumps in later course of time. And in 1916, again, Wolfgang Gale, in association with Langmuir, he developed what is called the vapor diffusion pump. Okay, regarding the vapor diffusion pump, we have a special session in which we will be discussing in detail about the working and the action of this pump. And these are some of the units, typical units used in vacuum technology to measure pressure. First one is millimeter of mercury. You are well familiar. In terms of height of mercury, you can measure the pressure, provided pressure is reasonably high. But in vacuum technology, you deal with very low pressures, okay, much less than 1 millimeter. Then we cannot depend on this unit. We may be dealing with 0.1 millimeter or 10⁻⁻10 millimeter, like that. Then these units become obsolete. And torr is another unit. 1 torr is equal to 1 millimeter of mercury, in fact. And bar is another one, that's equal to 750 millimeter of mercury, almost equal to 1 atmospheric pressure. 1 atmospheric pressure is actually 760 millimeter of mercury. But 1 bar is around 750 millimeter of mercury. There is a subtle difference between 1 bar and 1 Pascal. 1 Pascal is actually 1 Newton per meter square. Oh, sorry, 10⁵ Newton per meter square. And atmospheric pressure, 1 atmospheric pressure. Okay, that is equal to 760 millimeter per meter. These are all units used in vacuum technology in different contexts. Okay, and it is fun here for a reminder. Once again, we are emphasizing 1 torr is equal to 1 millimeter of mercury, and we will be mostly using this particular unit, 1 torr to 1 millimeter mercury. And another one is 1 atmosphere, which we will be rarely using, that's equal to 760 millimeter mercury or 760 torr. And third one is again 1 bar equal to 750 millimeter of mercury. There is a certain difference between 1 bar and 1 atmosphere. Okay, keep in mind. And we also introduced the concept of pressure regimes or pressure ranges, because different experiments can be done in different regimes. All experiments cannot be done in the same regime. Okay, certain experiments perhaps you can do during the interval 760 to 1 torr, some between 1 to 10 raised to minus 2, or some other you may be in the range of 10 raised to minus 10 to 10 raised to minus 12. For example, in a large hadron collider like one CERN lab, which may be dealing with the pressures like 10 raised to minus 2 to 10 raised to minus 10. But in a CRT2, for example, you may be happy with say 10 raised to minus 2 torr. Okay, so people have classified pressure ranges into regimes. Low vacuum, for example, it ranges from 760 torr to 1 torr. Medium vacuum ranges from 1 torr to 10 raised to minus 2 torr. And high vacuum ranges from 10 raised to minus 2 torr to 10 raised to minus 10 torr. And ultra high vacuum ranges from 10 raised to minus 10 to 10 raised to minus 12 torr. And extremely high vacuum is something less than 10 raised to minus 12 torr. It's rarely possible in experimental gadgets. And pressure ranges exist from 10 raised to minus 6 to say 10 raised to minus 17 torr in free space. And of course, in perfect vacuum, it is 0 torr, but it is not practically possible. But still, writing as a theoretical, in the theoretical context, we writing 0 torr as the perfect vacuum, which is not practically possible. So here is certain applications of vacuum. You may be asking, why do we use vacuum? One example is thin film fabrications. When we form thin films on certain surfaces, that surface should be free of gases. Otherwise, what may happen when the thin film is formed? For example, you form the film of aluminum. Suppose the phase is filled with oxygen, hydrogen, sulfur, like that. What happens? This aluminum may react with the sulfur, may react with oxygen, they may form oxides, sulfides, carbide, like that. Then the film will be obsolete. It cannot be used for the purpose which it is intended. Okay, its intended purpose may not be fulfilled once they form out. So the space in which the film formation takes place should be free of any gas. So we need a vacuum. And in particle accelerator, of course, you know, because we are accelerating particle like proton, electron, maybe neutron, like that, or any charged ions. So when they transit through free space, okay, they can easily reach the target. Suppose they are transiting through some gases, what may happen? These particles may collide with gas molecules or atoms, so their path may be deviated. They cannot reach the intended targets. Understand? So that is of no use. So in particle accelerators, free space vacuum is essential. Only then the ions or particles, charged particles, may be properly accelerated, properly guided. Understand? Another area is electric tubes and bulbs. You know, they need vacuum. Only then they will operate. Only the electron will be discharged. Electron will pass through the tube. Then only the fluorescence-like phenomena will happen. So another area is tubes and bulbs used to produce light sources. And in manufacturing of crystalline materials like ruby, okay, you know, jewelry and all, they use a lot of crystals. Understand? And nowadays in modern technology, that can be artificially prepared. Okay, when it is prepared in space, that space will be devoid of any gas. Otherwise, again, these molecules will react. We may not get the properly designed materials. Okay, may contain impurities, so its performance or quality may be degraded. Understand? So crystal design is a fabrication. Free space or vacuum is very important. And in pharmaceutical preparations, in antibiotics, hormones, vitamins, only it can be prepared in free space, or contamination may happen with the gas. The drug may be damaged. And in food preservation, no doubt, food preservation, vacuum required in order to avoid bacteria and other organisms, microorganisms that may deviate the food quality. And in freeze drying, okay. Freeze drying, what happens? Fully the material will be frozen down to very low temperature, so no microorganism can exist. So this is a typical vacuum chamber. Okay, you can see the gigantic thing. Usually in the physics labs, you can see a human being standing here. You can see that the walls are very thick, strong. Why this is so? Otherwise, what may happen? Atmospheric pressure is so high. Okay, so high, around 10⁵ per meter square. So the gas, this chamber may get crumbled. It is so too weak, too thin. So walls are made so thick so as to withstand high atmospheric pressure. So that's the reason why it is made so. It's a typical example which is given here. And in the subsequent module, we will be talking about different pumps, specifically about different pumps, in which the first one will be about oil-sealed rotary wave pump, second one will be oil diffusion pump, and third will be turbo molecular pump. Okay, each one will discuss in detail with its working principle and all. And the fourth one is about cryogenic pump. Okay, yet another very interesting pump used in very big modern scientific laboratories, advanced experiments. And another one is spectra ion pump, and finally Getter ion pump. Okay, these are some of the pumps which we will be dealing with in the subsequent modules. And here is some simple questions which you are expected to do as assignment. What is the SI unit of pressure? Okay. What is the commercial unit used in vacuum techniques? Okay, so we have discussed all these things. Give the scientific definition of vacuum. Give any two common applications of vacuum technology. And what do you mean by vacuum designs? Okay. So these are some of the questions which you are expected to answer and upload in the assignment section. So with these comments, I hope you enjoyed this session. Watch this video at least twice and try to answer the questions and upload properly in the assignment section. Okay, have a nice time. Thank you all.